Okay, let me make sure that everything is broadcasted. Okay, looks good. Okay, let's get started. Before I start, I will ask some review quizzes so that if you can answer most of these questions, perhaps you still remember what we introduced last week. Okay, first question. Illustrate an example in which using a traditional algorithm might be more appropriate than using a data-driven approach. Okay, so think about it. We gave some examples in the previous lecture. We talked about in certain situations, perhaps data-driven approach is better. In some other situations, perhaps the traditional algorithm is better. Okay, so any ideas you can think about it. So perhaps sorting 10,000 numbers. Okay, let's say 1 to 10,000. 10,000 numbers, they are mixed randomly, and how to sort these numbers from the smallest to the largest. Okay, that's probably we should do it using a traditional algorithm, sorting algorithm like bubble sort or quick sort, merge sort, or whichever. The reason is that we know how to do the sortings step by step. So that's why we said in this situation, perhaps traditional methods they might be better. Illustrate an example in which a data-driven approach might be more appropriate than a traditional algorithm. Okay, so if it's hard to enumerate all the rules, all the steps, then perhaps it's more appropriate to use a data-driven algorithm, and especially if labeling cost is low, but enumerating all the rules is very difficult. In this situation, data-driven approach is probably better. So for example, how to find a face in a photo, whether there's a face or not. Where's the face? Who is it? What's the gender? What's the age of this person? All these things. Okay, that's it's relatively more difficult to come up with a set of rules to identify a face. But labeling the face from images, that's relatively cheap. So perhaps we could label the images and let the computers learn the relationship between a face and what are the key components of a face. Okay, next question. Explain KNN. Okay. So last week we talked about two algorithms, one supervised algorithm, one unsupervised. And for supervised, we talk about KNN. So that's K nearest neighbors algorithm. So it's a classifier. It tries to predict the label of a new instance based on the neighbors. So essentially, you need to find in your training data which set of instances are the neighbors of the new instance, and then you look through the neighboring instances and what's the majority class in these neighboring instances, and that's probably your prediction. So the K here is a hyperparameter, if you still remember. That's used to specify how many neighboring instances you want to select. Okay, next question. Why features are usually scaled before using KNN? The reason is that if we don't scale the features, then it is likely that when we calculate the Euclidean distance, then the distance is dominated by a couple of features. Okay, so if we scale the features first, then every feature is in a similar scale. So in this situation, when you compute the distance between two instances, every feature plays roughly the same importance. Next, explain k-means. What is k-means? So k-means is a unsupervised learning algorithm. It is used for clustering. Right? Given some data partition, these data points into k groups, and you don't really have the labels. Okay? So basically, you just want the neighboring nodes to be within the same cluster, and we hope that the data points in different clusters they are far away from each other. But if two data points they belong to the same cluster, we want them to be close to each other. That's clustering. A k-means is a way to do the clustering. So how to do that? We randomly select k data points as the centroids, and then we can decide the boundary based on the k centroids. And then we will find that after the boundary is decided, we will find that the previously assumed k centroids, they are not the centroid for the current setting. Then you need to update the centroids. And after you update the centroids, it's likely that the boundary is wrong. Then you update the boundary. Then you just repeat these two steps until converge. Okay? Converge means that the boundary is fixed and the centroid is also fixed. And it is guaranteed that k-means algorithm will always converge, but it may converge to different results. Right? So sometimes we need to do the k-means clustering for a couple of times and then to decide which one is better. Okay, and we also talk about parameter versus hyperparameter. Okay, so we said that parameter is the unknown variables that your model needs to learn by itself. So for example, let's assume that let me open the pen. Okay. So in this example, if let's say this denotes, I originally want to say height and weight, but there's no negative height. So what can I say? This is anything that I don't know. Okay, let's assume this is height. Okay, and this is weight. This is height and this is weight. And if we and this data, these are the observed data points. And if we assume that the relationship between h and w follow this formula, which means that when y is w, then w equals to a multiplied by this h plus b. And we want to find the best a and best b such that this line goes through most of the data points. Okay, and in this case, computers will try to identify what are the proper A and proper B. Now, we will talk more about this a couple of weeks later. But now, at least we know that A and B should be decided by the computer, and that's what we call it by learning. And since A and B are decided by computer, they are the parameters. On the other hand, hyperparameter is the variables decided manually by the programmer, by you, okay, by human. So for example, in KNN, this K is a hyperparameter, okay, because K is decided by the user. You need to specify how many neighboring training instances you want to referenced. Okay, but even having said that, sometimes we may abuse these terms. For example, in conversation, we might say that let's fine-tune the parameters to improve the performance. Okay, so if we want to be very careful, this should be hyperparameter, not parameter, right? Because hyperparameter can be fine-tuned by human beings, but parameters is decided by computers, so they cannot be fine-tuned by us. So in this, based on the context, you should know that this parameter actually means hyperparameter. Okay, but sometimes we abuse these terms. So you need to decide what does this parameter mean based on the context. Okay, next, dealing with ties in KNN. So we said that KNN is based on a simple intuition. That is, we decide the label of the new instance based on the neighboring neighboring data points in the training data. Okay, so it is possible that if we are dealing with a binary classification problem, it's possible that half of them vote for yes, half of them vote for no, then we have a tie. Or even in the let's say trinary classification problem, which means we have three classes. It is also possible that if we use KNN and K equals to 3, then it is possible that each of the three classes get 1 vote. So again, you have a tie. So how to break the tie? Okay, so here are two widely used simple and common practices. One is you just randomly select a class. Okay, so if there's a tie, you just randomly select one from the ties. And the other is you could gradually decrease the K by 1 until you break the tie, and you will have a winner. Right, so you just pick that winner. And I think last week we talked about KNN, and our KNN assumes that all the neighboring nodes, they have the same weight. They have the same influence for your model to predict the target. Okay, so if we set K to 3, then essentially we find the 3 nearest neighbors, and each one of these 3 neighbors, they play the same role. And they are equally important. But in fact, we could assign different weights to different neighbors. Okay, and a common approach is to weigh the neighbors based on the inverse of the distance. Okay, so for example, let's say again we want to use the height to predict the maybe gender. Okay, gender. So height and weight to predict gender. Okay. So we have some, let's say, males here and females here. Okay, and then if we want to, we have a new instance here. This is a new instance. Whether this star is a male or female. And previously, when we said we use KNN, let's say we select K equals to 3, for example, then perhaps these 3 are the nearest neighbors of this star. Okay, and each one of these 3 instances, they are equally important. But if we use weight, perhaps this is closer, these 2 are farther, then this one would have a higher weight. Okay, that's a weighted version of KNN, and there are a couple of variations, so you could use that too. Next, how to evaluate the clustering result. So we said that clustering is a unsupervised learning algorithm, which means that there's no ground truth about the labels. So in this case, how to evaluate the clustering result? Okay, so first, there's no correct answer for clustering because there's no label. So whether evaluating the clustering result is a reasonable measurement or not, it's a question by itself. It's debatable. But if you really want to somehow quantify if you really want to have a quantified measurement, then one possible way is to compute the ratio between intercluster distance and the intracluster distance. And a large ratio means that a larger ratio means that intercluster distance is larger and intra-class distance is smaller, which means that the data points in different clusters, they are farther away. Data points in the same distance, they are closer. So that's probably what we want. Okay, so a larger intercluster distance divided by the intra-cluster distance. If the result is larger, then that probably means you have a better clustering results. And how to define the intercluster and intra-cluster distance? There are a couple of ways, and here we introduce one simple way to do it. Okay, so let's assume that we have 7 data points, and this is their xi. Okay, xi1, x1 is 1, x2 is 2, and so on. And their corresponding labels. Okay, so y1 is blue, y2 is blue. Okay, y3 is blue, and this is 1, 2, 3, 4. This is x5. x5 is 9. x6 is 10. x7 is 11. And this is y5, which is red. y5 is red. y6 is red. Okay, here perhaps I should not use y because it's a clustering algorithm. Perhaps I should say that based on a certain clustering algorithm, all these 4 data points belongs to cluster number 1, and all the 3 data points belongs to cluster number 2. Okay, and I use the blue and red to denote that they belong to different clusters. So what's the intercluster distance? Okay, so we just compute the average. So the average from 1 data point in cluster number 1 to 1 data point to cluster number 2. Okay, so the distance between this 1 and this 9 is 8. Okay, and 1 to 10 is 9. 1 to 11 is 10. Okay, likewise 2 to 9 is 7. Okay, and so on. So we have 4 multiplied by 3, which means we should have 12 distance measures here, and we divide it by 12. So this is the result. This is the average intercluster distance, which means the average distance from one data point in this cluster to a data point to another cluster. So what is the average intra-cluster distance? So that's the average distance between 2 data points within the same cluster. Okay, so here we have distance between 1 to 2, which is 1, 1 to 3, which is 2, 1 to 4, which is 3. Okay, and then we have 2 to 3, which is 1, 2 to 4, which is 2, 3 to 4, which is 1, and so on. And again, we have 3 intra-cluster distances. 9 to 10 is 1, 9 to 11 is 2, and 10 to 11 is 1. Okay, and we have 9 such numbers, so the average intra-cluster distance is 14 divided by 9. So the ratio is inter-cluster distance divided by the intra-cluster distance, which gives us this number. Okay, so if this is larger, that means intercluster distance is larger, which is what we want. And that might also mean that the intra-cluster distance is smaller, which again is what we want. Okay, so when this value is larger, perhaps that means we have a better clustering result. Okay, so this is an illustration that if a certain clustering algorithm it decides these 4 data points belongs to cluster 1, and the other 3 data points belongs to cluster 2. If this is the result, then of course the intercluster distance and the intra-cluster distance will be different. In the above, so if we compute, if we compute the intercluster distance, there would be, let's see, 1 to 4, which is 3. 1 to 10, which is 9. 1 to 11, which is 10. And then 2 to 4, which is 2. 2 to 10, which is 8. 2 to 11, which is 9. Okay, likewise 9 to 4, which is 1. 9 to 10, I'm sorry, not 9. 3 to 10, which is 7. 3 to 11, which is 8. Okay, and finally this 9 to 4 is 5. 9 to 10 is 1. 9 to 11, so this is wrong, right? This is 2. Okay, and I don't know if the result is the same or different, but this one should be 2 because the distance between 9 and 11 should be 2. Okay, so we should change this to 2. And then you can compute the average. I'm not sure whether this is right or wrong. If that's wrong, then you can correct it to the correct answer. It should be straightforward. Okay, and then you could also compute the intra-cluster distance, and this is the ratio. And compared to the previous one, this one is larger. This one is smaller. And if you look at the clustering result, then it seems, at least for most people, I believe that the previous one should be a better clustering result because the nodes in the data points in the same cluster, they are closer to each other. Okay. Oh, and last week one student asked about how to do the KNN or K-means with categorical features. Okay, so let's think about it. KNN and K-means, a fundamental thing they need to be able to compute is the distance between two data points based on their features, right? For KNN, you need to find the K-nearest neighbors based on the features. For K-means, you need to be able to compute distance from the centroids to some other points, data points. So again, you need to be able to compute the distance between two nodes or two data points based on the feature. So if all the features or some of the features are categorical features, then how to define the distance? Okay, it seems that it's not that straightforward. Okay, so how do you define the? So let me look at the. Oh, okay. So here we have an example. Let's assume we have a categorical feature called nationality, and the feature values include UK, Japan, and Mexico. Okay, so if you somehow encode UK as 1, Japan as 2, and Mexico as 3, for example, if we encode, so this might be one way to convert the categorical feature into numbers. Okay, I just convert UK to 1, Japan to 2, and Mexico to 3. But in this situation, by this encoding, you are assuming that the distance between UK and Japan, which is 1 to 2, is smaller than the distance between UK and Mexico, which is the distance between 1 and 3. Okay, so does that make sense or not? That depends on your application domain, but very likely it's probably not a valid assumption. The reason is that unless in your application domain, UK and Japan are indeed closer, UK and Mexico are indeed further away. Otherwise, you encode this way, you are assuming that the distance between them are different, and that's decided by the way you encode the data. Okay, so that probably doesn't make sense. And so a proper way to do it, or a more common way to convert the categorical features into some other form, is using the one-hot encoding. So the UK is converted into 100, Japan is 010, and Mexico is 001, for example. So the first feature can be regarded as UK or not. Oh, actually I wrote it here, UK or not. The second feature becomes Japan or not. The third feature becomes Mexico or not, right? So that's why UK, we use 3 features to denote UK, which is 100, because now we have an UK, but not Japan and not Mexico. And Japan is 010 because this means not UK, this means Japan. Okay? So that's called one-hot encoding because one of the K features will be on. If you have K distinct feature values, okay, so this is a categorical feature and it has K distinct feature values, then we could convert this feature to a vector with length K. And most of them will be 0, only one of them will be 1. Okay, that's one-hot encoding. Okay, but on the other hand, if you could somehow define the distance based on the categorical features, then perhaps you could do it. For example, if one of the feature, height, it has three values. It's a categorical data, and its values are tall, average, and short. Okay, so that means the distance between these two should be smaller than the distance between these two, because this, although they are categories, but they have some sequence. Okay, there are some sequence information inside these categories. So in this situation, you could say that perhaps you could say that tall is 3, average is 2, and short is 1. Then the sequence still follow our intuition. Oh, and finally, start from our next lecture, we will start to use a hybrid way for lecturing. Hybrid means that we will have both physical course in class, and at the same time we will still keep the YouTube streaming like what we are doing right now. So you may choose whichever comfortable to you, but we still encourage you to participate online because if you really want to be in class, we probably need to record your seats every week, you know that. So there are some policies. We need to know every student's seat in every week. So in case something happened, we know who should be informed for some information. Okay, so I still encourage you to stay at home or stay at your dormitory and just watch the YouTube streaming, just like what you are doing right now. But if you really want to be in class physically, you can do that. Okay, because we get some requests asking me or asking the TA, can we have a physical class? Some of the students really want to be in a physical room. Okay, so starting from next time, we will have a hybrid class. But if you really, if you attend physically, then of course you need to still follow the government rules. Okay, which is I think no food, wearing a mask, and you need to have some social distance to some of your classmates. All those kind of things. Okay, and also for the midterm and final, because we have a midterm and final presentation. So I think for those 2 weeks, you probably need to be physically in class, or perhaps, let me think about it. Perhaps we could divide all the students into 2 groups, and we will present a midterm in 2 consecutive weeks, and the final in 2 consecutive weeks, and then for every presentation week, only half of the students need to be physically appear in the classroom. Perhaps we will do that. Let me discuss with the TAs, and I'll let you know our final decisions. Okay, so let's review for what we talked about last week. Let me check if there's any questions on the chat room. Okay, there's no questions, so let me move on. Let's see. Last time we stopped at we finished the KNN and K-means, so we will talk about the distance measures this week. We'll start from here. But before I move on, let me make sure that where's my cursor? Let me make sure that the OBS captures the right PowerPoint. Let's see. Sorry, there's something wrong in the OBS, so I have to figure out how to do that. Okay, so here it is. Okay, this should work. I think it's broadcasting right now. I think it's broadcasting my desktop. Okay, yeah. Okay, so last week we talked about KNN and K-means, and both methods they depend on how you define the distance between data points. And so this week I will start by introducing some distance measures. Okay, so here are some properties of a distance measure. Okay, so a distance measure, okay, so let's say x and y are two data points. So the distance between x and y should be non-negative. Okay, it should be 0 or positive. The next property, the distance between x and y is 0 if and only if x is y. Okay, so if and only if means that if the distance between x and y is 0, that means x is y, and on the and the vice versa is, or the reverse is also true. If x is y, then the distance between x and y is 0. The third property, the distance from x to y equals to y to x. So this is, I'm probably at a triangle mark here because some distance measures doesn't really follow this property. Some distance measures are asymmetric. Asymmetric means that the distance from x to y doesn't equal to y to x. Okay. But most of the distance measures, they follow the third property. Okay. Finally, triangle inequality. Okay. The distance from x to y is smaller than distance from x to z plus z to y. Okay, so let's introduce some of the most famous distance measures. The first one is Euclidean distance, which is probably the most straightforward way to define the distance between two data points, x and y. Okay, so here we assume that x is x1 up to xd, for example. Okay, that's a column vector. And y is y1 up to yd. Okay, these are two data points. And so the distance between them is, where is it? Okay, oh, I didn't list the okay, so I just write it using text. So square root of the sum of squares, so that means x1 minus y1 square plus blah, 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 plus xd minus yd square, and then square root. Okay, this is the distance between x and y. And it is also called the L2 norm. And the other thing called Manhattan distance. Manhattan distance is, again, if we have x is x1 to xd, and y is y1 to yd, then their distance is s1 minus y1 plus the absolute value of x2 minus y2 dot 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 up to xd minus yd. Okay, so this is L1 norm. Okay, and it is called Manhattan distance because if you think about it, Manhattan is the Manhattan street is sort of like a grid structure. Okay, they have this is the map of Manhattan City. Okay, they have the First Avenue, Second Avenue, Third Avenue, up to like 11th or 12th Avenue. Okay, and then here they have the First Street, Second Street, Third Street, up to, I don't know, several hundred street. So how to move from one data point to another data point? It's sort of like you have to move. It's sort of like you move from here to here and then here to here, right? So that's why it is called the Manhattan distance. If the data point here is 2 and 11, for example, And if the coordinate here is like, let's say 3 and 13. Okay, then move, what's the distance to move from here to here? Okay, you have to go from here to here and here to here. So from here to here, that's 3 multiplied by 2. From here to here, that's 13 multiplied, 13 subtract 11. Okay, so that resembles our formula here. So that's why it's called Manhattan distance. Okay, so here's an example. If we have data point A is 5, 5, data point B is 9 and 8, then the L2 norm is like this, and the L1 norm is simply this 9 subtract 5 and take the absolute value plus 8 subtract 5 and take the absolute value. So give us 7. Okay, so we know what is L2 norm, we know what is L1 norm. Now let's introduce something called L infinity norm. So L infinity norm is, okay, and oops. Again, x is x1 to xd, y is y1 to yd. They denote 2 data points. And the distance between x and y would be s1 subtract y1. This is one thing. x2 subtract y2, that's one thing, and so on up to xd subtract yd. And then you see, compute whichever is the max among these things. Whichever is the max, that's your result. Oh, by the way, the max here should be, how should I denote it? Whichever, how should I denote it? Maybe let me show you the formula, and you probably can, you probably know what I mean by, so the max here is not very accurate, but let me show you the formula of Li norm. And then let's come back to L infinity norm. Li norm between x and y is xi minus y, xy minus y1 to the power of I plus x2 minus y2 to the power of I plus dot 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 up to xd subtract yd to the power of I, and then take the ith root. This is the definition of Li norm. So if I equals to 1, then we have what? We have, this should be absolute value. Here should be absolute value. Okay? So if I is 1, then what do we have? Then we come back to the L1 norm. So the L1 norm is simply what we said, summation x, let me use j because I have I here, xj subtract yj, j from 1 to d, right? And if I equals to 2, then based on this formula, we have xj subtract yj square. Okay, we have absolute or not, doesn't matter because we have a square here. Okay, and then take the square root, summation j from 1 to d. Okay, so again, this is the same as our previously introduced L2 norm. And how about a equals to infinity? A is infinity means that we have x1 minus y1 to infinity plus x2 minus y2 to infinity plus dot 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 up to xd subtract yd to the power of infinity. And then we have to take the take the root, but I'm sorry, take the infinitesimal root. Okay, so what's this? Let's look at it. So we take something to the power of infinity. Okay, let's say let's assume that without taking the infinity, if this is the largest, if x, the distance between x1 and y1 is the largest among all the xi, yi's, among all the xi subtract yi's, then when we take it to the infinity, this one would be much larger than the others, right? So let's assume that if for a certain x k minus yk, if certain is the largest among all x j subtract y j. Okay, if this is the largest one, then sk to the power of infinity for all j not equal to k, right? So that means this entire thing will be, let me erase something. Eraser. So that means if xk minus yk is the largest, then that means where's the pen? Okay, so that means this will be roughly the same as sk subtract yk to the power of infinity, and the others are close to 0 because this one is much larger than the others. And then here, so we would end up having sk subtract yk. Okay. Oh, so here I should use absolute value. Okay, so that's why L infinite norm is the same as choosing the max among all these things. Okay, so previously, just a couple of minutes ago, I said I was wrong because here there should be an absolute value. Okay, does it make sense? Okay, let's continue. Okay, so here is just explaining what is LK norm or Ln norm, and why L infinity norm is the maximum of the difference between x and y in any dimension. Okay, so next let's talk about Jacquard distance. Okay, so Jacquard distance is used to measure the distance between sets. So how do you define the sets between P1 and P2? Okay, they denote two different sets. Okay, so one possible way is first compute the interaction, the length of the interaction. So the intersection, not interaction, sorry, intersection. So intersection is A, D, and E. Okay, so the size of the intersection is 3. The size of the union is A, C, D, E, which is 4. Okay, so the Jacquard distance is 3 divided. I'm sorry, Jacquard similarity is 3 divided by 4. And Jacquard distance is simply one subtract Jacquard similarity, so it gives us a quarter. Jacquard distance is a distance measure because, well, first, why is dyy 0? Because, well, the Jacquard similarity between x and x, if these are both, if x is a set, then a set to itself, the Jacquard similarity is always 1. So the Jacquard distance 1 subtract 1 is 0. Okay. Distance from x to y is y to x. Okay, so this is trivial because the union and the intersection, they are both symmetric. Okay, distance is always positive or I should say non-negative, okay, because the size of the union is always smaller or equal to the size of the intersection, and the size is always non-negative. Okay, so that's why this is always larger than 1. Okay, and finally, for the triangular inequality, it still holds, but we don't give a proof here. Okay, cosine distance. What is cosine distance? Cosine distance is used to measure the distance between two vectors. Okay. So, for example, let's say the first vector is 1, 3. The second vector is 3 and -1. So what's the distance or cosine distance between them? So the cosine distance measure the angle between them. So 1, 3 is here. Right? 2, 3, 1, 2, 3. 1, 3 is here. This is P1. And P2 is 3, -1, 3, 1, 2, 3, and -1. This is P2. And cosine distance is sort of measured in this theta. So how to do that? Okay, so you should probably learn this in high school. So we have, in the numerator, we have P1 dot P2. In the denominator, we have the norm of P2 multiplied by the norm of P1. Okay, so P1 dot P2 is 3 subtract 3, which is 0. And the norm of P1 is 3 squared plus 1 squared, and take the square root, which is 2. And P2 is again 3 squares plus -1 squared and square root, which is 10, square root of 10. Okay, so we end up having 0 divided by 2 times the square root of 10, which gives us 0. Okay, so that is so the cosine distance is 0, which means these two, so if we really compute cosine 90 degree give us 0. Okay, so that means this theta is in fact 90 degree. Okay, so if you have two distance which is two vectors which is like this, they are they are identical, 1, 0 and 1, 0, for example. Okay, then their cosine distance would be exactly 1 because they are exactly the same. Okay, you can plug in where is it, this formula, you will get 1. Okay, so the distance between P1 and P2. Okay, so another way to think about it, perhaps geometrically, is that P1 dot P2 can be considered as the length. You just project P1 onto P2. So P1 dot P2 is sort of like you project this P1 onto this onto P2, and then you will have, so the length of P1 dot P2 is like this multiplied by this, and then we divide it by the length of P2, so that would end up giving us simply like a normalized score of the projection multiplied by this. So it's sort of like you project P1 onto some direction and normalize normalize this result by P2. Okay, and cosine distance is again it follows some of these properties, and I will skip it here. So essentially, distance between x and x is 0. Distance from x to y is y to x. All these things, they all follow. It follows all these things. Okay, so it's now 2:51. I'll take a 10 minutes break. We'll come back to 3:01. the feature is defined somehow in based on set. Okay, so set means that let's say the first instance is set number 1, and it's let me open the pen. Okay, let's say the first instance is a set, okay, and it includes A, B, C, 3 elements. The second second instance is another set. It includes A, C, D. Okay, and X3 is yet another set, includes B, C, D, E. Okay, and they have some corresponding labels. Y1 is 1, Y2 is 3. I'm sorry, 0. Let's say 1 or 0, binary classification. Y3 is 1. Okay, and then you're given a X star, which is a new instance. You want to predict its corresponding label, and let's assume it's it includes 2 elements, B and C. Okay, by KNN you need to define the distance between x1 and x star, x2 and x star, x3 and x star, and find the k-nearest neighbors. So how do you define the distance between x1 and x star? If you use Euclidean distance, you just cannot compute the distance, because Euclidean distance is not defined based on set. However, if you use the Jaccard distance, which is defined earlier, okay, then the distance between x1 and x star can be defined by one subject Jaccard similarity, okay, which is the size of, let me write it very clearly, A, B, C, B, C, right? So you end up at one subject, ABC and BC, the union, the intersect is only B and C, so the size is 2. ABC union BC, so it's ABC, the size is 3. So you end up having the distance is 1 divided by 3. Okay, so likewise you can define the distance between x2 and x star, and so on. And then you can find the k-nearest neighbors of x star, and you can make the prediction based on the corresponding y's. Okay, so sometimes we need to have other distance functions. That's why I want to introduce some other distance functions here. I'm sorry, I just found that I have a low battery on my laptop, so let me grab the power plug very soon. Okay, let's continue. Okay, the next one is edit distance. Okay, so let me erase everything here, because all the things I just introduced, they have nothing to do with edit distance. Okay, so edit distance between 2 strings is the number of inserts and deletes that are required to turn from one string to another. Okay, so let's look at an example. If the first string is A, B, C, D, E, the second string is B, C, D, U, V, E, then how many inserts and deletes are needed to convert X to Y? So we need to delete this A, that's one step, and then we need to insert U at here, and then we need to insert V here. Okay, so we will end up having B, C, D, U, V, E. Okay, so that means 1 deletion and 2 insertion, so the edit distance is 3. Okay, and here is another way to do it. So you basically, the distance between x and y can also computed by the length of x plus the length of y, subtract 2 times longest common subsequence, the length of longest common subsequence. Okay, so here the longest common subsequence is B, C, D, E, right? B, C, D, E. That's the longest common sequence. So based on our previous formula, the length of X is 5 because we have 5 characters here. The length of Y is 6. And the length of the longest common subsequence is 4. So subtract 2 multiplied by 4. So this gives us 3, which is the same as the number we computed here. And again, here shows why edit distance follow the properties we introduced in the very beginning. Okay. I'll skip the details. And a variation of the edit distance could be, so previously we said that edit distance between two strings we allow only insertion and deletion, but perhaps we could also allow mutate. Okay, so mutate means change one character into another character. Okay, so if we allow these 3 different previously we allow only insert and delete. Now we add one extra supported operation, which is mutate. Okay, so that means if you ask me the distance between A, B, C, and the distance between A, D, C, for example, if we use the original edit distance, we need to delete B and add D, which means the edit distance is 2. But if we use if we allow the mutate operation, then turning ABC to ADC requires only changing this B to D. So that means 1 operation. So the variant edit distance becomes 1. Okay, next, Hamming distance. It's a number of positions in which the bits are different. So for example, we have 1, 0, 1, 0, 1. Here we have 1, 0, 0, 1, 1. How many bits are different? So the first bit is the same, the second bit is the same, the third bit is different. Okay, the fourth bit is also different, but the fifth bit is the same. Okay, so the Hamming distance is 2. Again, here shows why Hamming distance follows many of the properties we introduced in the very beginning. Okay, there are other distances. For example, KL divergence. This is a very well-known asymmetric distance. It is used to measure the distance between 2 distributions. Okay, so for example, if you have, let's say in case 1, you have this is your first distribution, f of x. This is your second distribution, for example. This is f of this is f1 of x, this is f2 of x. Okay, so you have 2 different distributions, and it looks like they look more or less similar. So the KL divergence between these two distributions should be very low. Okay, their distance is small, and KL divergence is sort of measuring the distance between 2 distributions. On the other hand, if your f1 of x is like this, I'm sorry, let me draw it again. If your f1 of x is like this, this is your f1 of x. If your f2 of x is like this, then they are very different. Whenever f1 of x is low, f2 of x is high. Whenever f1 of x is high, f2 of x is low. So they are very different. So in this case, the KL divergence between these 2 distributions will be large. And it's asymmetric because, interestingly, let's forget all these figures and keep only this figure. Let's say this is f1 of x and f2 of x. They are 2 distributions. Interestingly, the KL divergence between from f1 to f2 does not equal to KL divergence from f2 to f1. I don't want to list the detailed formula here, but 没有同步到是什么意思？
对，就是他们说现在 edit， 然后现在还在这个画面。
为什么会这样子？所以从什么时候开始？
4分钟了。
第16页。
对，这一堂课一开始的时候是有同步到的吗？
有。
Okay, so the TA comes to my office and telling me that the screen and my voice, they are not synced for some unknown reason. So I have to set up the OBS again. But when did that happen? Is that working now?
那时候这堂课开始，他说好像学弟是说从这堂课开始就只有声音同步了。
从这堂课开始是说从今天的一开始，还是说从这一个第2堂课开始啊？Okay, so the TA told me that there's somehow the screen was not broadcasted correctly. But since when? Can anyone leave comments on
他说第
the?
2堂课开始。是同步的。他说第2堂课开始。
Okay, since the second class. Okay. Okay, so where are we? Let's see.
Edit this.
Yeah. I know where I started, but I have to find that slide. Yeah. Okay, thank you. Okay, so okay, so in the very beginning, I just said that the reason why I need to introduce several different distance measures is because Euclidean distance is not the only distance definition. And to do the KNN or K-means, we need to compute the distance between different data points based on the features. And so I gave an example earlier, and unfortunately it was not broadcasted, so let me write it briefly again. So perhaps let's use the Jacquard distance here. Okay, let's assume that in our training data, our axes are defined by sets. So x1 is A, C, D, for example. x2 is A, C, E, for example. x3 is D and F, okay, for example. And their corresponding y's, let's assume this is a binary classification problem. So y1 is 0. Let's say y2 is also 0, and y3 is 1, and so on. We have several y's up to, let's say, xn and yn. Okay, so now you are given a new instance x star. You want to predict the label of this x star, and x star is a set which contains, let's say, a and e. Then I need to compute the distance between this x star to all the x's in the training data, right? So I can find the k-nearest neighbors if I want to use k and n. So in this case, I simply cannot use Euclidean distance because Euclidean distance is not defined on sets. Okay, but if I use the Jacquard distance, then I can compute the distance between x star and all the x's in the training data. For example, if I want to compute the distance between x1 and x star, so star is here, x star, then that would be 1 subtract the Jacquard similarity between x1 and x star. Okay, and Jacquard similarity between x1 and x star would be, let me write very clear, that would be x1 includes a, c, d. So there would be set A, C, D, intersect set what's x star? X star is ANE. ANE. Okay, the size of this intersection divided by anything wrong? The TA comes in again.
OBS is still on the edit distance there.
What's going on here? What happened today? That's really annoying.
Maybe it's OBS.
OBS. Let me. What can I do? That's so annoying. I still need to full screen first, and then it's not here.
Or
It's not here. Can I restart OBS and still connect to YouTube in this situation? Can I restart the OBS? It should be okay as long as we have the key, right? The code.
yeah.
Okay, so let me restart the OBS and see if it works. I should stop the streaming first.
Streaming.
I will stop the streaming for a couple of minutes because we need to reset the. Okay, let's try it again. Let me try to go to other pages and see if that would work on OBS. It looks like it's working. Okay, let's continue. Okay. So this is a third cut. Third cut. Okay. Let me open the pen. Okay, I said that we have x1, which is A, C, E, and we have a corresponding yi, which let's say 1. There would be like 10 minutes or 10 seconds or 20 seconds delay, so you will not see what I wrote on the screen immediately. I was talking to the TAs because they are afraid that because I have already said something, they heard what I said in live, but they cannot see any response on their phone, so they thought there might be something wrong again. But I told them they should be okay this time because there's a 20 seconds, 30 seconds delay. Okay, let's continue. Okay, x1 is a set, and its corresponding y1 is 1. Let's say the second instance, the feature is A and E, for example, and y2 is also 1. And let's say x3 is B, C, D, and y3 is 0, and so on, up to let's say xn. Sn is B, whatever. Okay. So these are the training data, and if you are given a new instance x star, we need to if we want to use KNN to predict the corresponding label of x star. Let's say x star is B and E. Okay, so we need to compute the distance between x star to all the x's in the training data. And apparently, the distance between one set to another set cannot be computed by Euclidean distance. Okay, but we can use Jacquard distance. So in this case, for example, the Jacquard distance between x1 and x star would be 1 subtract the Jacquard similarity between x1 and x star, which would be 1 subtract in the numerator that should be the union of x1 and x star. So that should be ACE intersect x star is B and E, right? And in the denominator, we should have ACE union B and E. Okay? So there will be one subtract ACE intersect BE. That gives us only 1. Right? So that will be just this E. Okay, so it's 1. ACE and BE union, there would be ABCE. So that's 4. So, I'm sorry, 3 divided by 4. Okay? So this is the Jacquard distance between x1 and x star. So likewise, you can compute the distance between x star to all the x's in the training data. Then you can find the k-nearest neighbors and you can make prediction based on majority voting. So cases, then in many cases you need to use different similarity measures. Okay, so let's quickly fast forward to edit distance, which is let me make sure OBS is running correctly. Okay. So edit distance, it's defined. So it used to define the distance between two strings, and it's a number of inserts and deletes to convert one string into another string. So for example, if this is string 1, this is string 2, how to convert from x to y based on insertion and deletion. Okay, so you need to convert x to y. First you need to delete this a, right? And then B, C, D are the same, so you need to insert a U here, and then you need to insert a V. So that means you need 1 deletion and 2 insertions, which means 3 differences. So the edit distance is 3. And the other way to compute it is the length of x plus the length of y subtract 2 times longest common subsequence. Okay, so let's see. The longest common subsequence between this x and y would be BCDE, right here. BCDE. That's the longest common subsequence. Okay, so based on our previous formula, the length of x is 5. The length of y is 6. The longest common subsequence is, the length of the longest common subsequence is 4. So the result is 3, which is the same as the number of insertions plus the number of deletions. And here explains why edit distance is a distance measure. And there could be some variance. For example, if we include one more operation, which is mutate. Mutate means replace one character by another character. Okay, so in this case, if you compute the distance between, for example, ABC and ADC, okay, if we use the original edit distance, then from ABC to ADC, you need to first delete B and then insert D. So the distance should be 2. But if we include one more operation, which is this mutate, then we could replace B by D directly. Then the distance becomes 1. Okay, and Hamming distance. Hamming distance simply computes the number of bits that are different. So bit 1 in both P1 and P2, they are 1. Okay, so that's the same. The second bit are both 0. The third bit are different, right? Third bit. The fourth bit is also different. And the fifth bit is the same. So the Hamming distance is 2 because the third bit and the fourth bit are different. Again, this Hamming distance is a similarity measure. So there are other similarity measures, and I introduced earlier, and let me repeat it again because somehow my screen was not broadcasted. So KL divergence is used to define the distance between two distributions. For example, if this is the first distribution f1 of x, if this is the second distribution f2 of x, f2 of x, then visually, at least visually, it looks like f1 and f2 are very similar. So their KL divergence should be small. On the other hand, if f1 of x is like this is f1 of x. If your f2 of x is like this is your f2 of x. Then f1 and f2 are very similar. Very different. Whenever f2 is small, f1 is large. Whenever f2 is large, f1 is small. So they are very different. In this case, the KL divergence between f1 and f2 would be large. And KL divergence is asymmetric, which means that the KL divergence from f1 to f2, usually we roll like this. It's unequal to KL divergence from f2 to f1. They are not equal. But I don't want to show you the equation, the exact equation. I just want to let you know that there are various different similarity measures, and some of them are asymmetric. Okay, and now consider a case. Okay, if you want to define the distance between, let's say, let's say you play the chess game. You play the chess, okay, and how to so you want to find what's the best next move, for example, and perhaps one way to do it is you just go back to your database and check which board situation is most close to your current board situation. Okay, so you need to define the distance between two board situations if you play the game of chess. Okay, so perhaps you need to define the distance between, let's say you have a king here, and in another board you have a king here. So you want to define how similar or how different these two boards look like. Okay, then perhaps you could define the distance based on the distance of the king. Okay, so how to move the king from one place to another. Okay, so if you know how to play chess, king can only move to one step to its neighboring eight grids. So it can only move to here, 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 and here. So it has 8 possible ways to move, all its neighboring grids. Okay. So the distance from one place to another, okay, I just copy this here. Let's assume that you want to move a king from here to here, for example. Then you need to move like this and this, okay? So it turned out that this is the infinity norm. L infinity norm. Okay, some quiz. Given an example in which Euclidean distance may be inapplicable or inappropriate. So inapplicable means that Euclidean distance just cannot be used. So we just gave one example, right? How to define the distance between two sets. S1 is A, B, C. Set 2 is A, C, E. Okay, how to define the distance? You just cannot use Euclidean distance. So that's an example where Euclidean distance is inapplicable. How about it's applicable but inappropriate? Okay, so let's see. So assume you have one. I think I have an example somewhere. Yes, okay, so let me use this one as an example. Suppose document 1 has 100 word 1 and 300 word 2. Document 2 has 10 words 1 and 30 words 2. Document 3 has 101 word 1 and 20 word 2. Then which pair of document, which document is more similar to document number 1? Okay, so think about that for a second. And then I hope that your answer should be, I think, doc number 2. Right, because let's say maybe this is a book about Harry Potter. So that word 1 is Harry Potter. Okay. Word 2 is I don't know, Gryffindor. I don't know how to spell that. Gryffindor. Okay, Gryffindor. Okay, and then document 2 is probably a summary of this book, right? That's why the word appearance frequency of word 1 and word 2 are the same as the word frequency of document 1. Okay, and document 3 is probably something else. Okay, it's probably another book, and so it has different word frequency. So in this situation, if you use the Euclidean distance, okay, Euclidean distance, doc 1, this is word 1 and word 2, okay? So 100 and 300, 100 and 300. This is doc 1. Doc 2 is 10 and 30, 10 and 30, which is here. This is doc 2. Doc 3 is 101 word 1 and 200 word 2. 101, 200, probably here. This is doc 2. Doc 3, right? So if you use the Euclidean distance, then doc 1 and doc 3 are closer. However, if you use the cosine distance, then doc 1 would be like this. Doc 2 will be like this. Doc 3 will be like this. And you can see that the degree between doc 1 and doc 2 is 0. So they are very, very close. Okay? So if we use the cosine similarity, then doc 2 is closer to doc 1. So apparently using different similarity measures, you would end up having different results. And depends on your application domain, you may need to use different similarity measures. Whichever is more appropriate, that depends on your application domain. And I think in the NLP domain, usually cosine similarity is more widely used. Okay, we go back to the second quiz. How to define the distance between two sets? Okay, we just talked about it, right? You could use the, for example, the Jaccard distance. Okay. Okay. Now let's finish the discussion of the distance measures. Let's move on to the next slide. And let me make sure OBS captures my screen. Okay, good. Okay, let me continue. So now I want to talk about, I finished talk about K-earned and K-means and some of the similarity measures finally. So now I want to talk about decision trees algorithm. But to talk about decision tree, I need to introduce something called entropy. And then I can, this is sort of like a prerequisite knowledge. So after you know what is entropy, then we can start to talk about decision trees algorithm. Okay, so what is entropy? Okay, so let me give you some history. Shenlong, a very famous scientist, and he looks very handsome. So His master thesis, a symbolic analysis of relay and switching circuit. So it's sort of like the fundamental thing of the today's computer. Okay, so it is this. Some people say that this is the probably the most important and the most noted master's thesis in the 20th century. Okay, this is his master's thesis, and basically it describes the fundamental component of today's computer. But we don't want to talk about this thesis today. We want to talk about another great piece of work written by Shannon, which is a mathematical theory of communication. Okay, so in this paper, Shannon developed the concept of information theory. And he developed a thing called information entropy, and it's a measurement of uncertainty in a message. So this is the sometimes people call Shannon as the father of information theory because of this paper. So how to measure information? If you observe if you observe the occurrence of a certain event E with probability P, then how much information you get? So Shannon believes that you should measure the information, the amount of information, based on probability, not based on the event itself. You should based on probability. The reason is that if a certain thing is unlikely to happen, but it happens, then this piece of information, this piece of thing should contain a lot of information. It's unlikely to happen, but it indeed happened, then there should be a lot of information. If a certain thing is almost guaranteed to happen and you tell me that it happens, then you told me almost nothing. Okay, that's his idea. So if you have two events E1 and E2 and their occurrence chances are both P, then observing E1 and observing E2 reveals the same amount of information. That's Shannon's idea. So maybe let me give you some more examples. If I tell you that the sun will rise from the east tomorrow, it's almost guaranteed to happen, right? The sun is almost guaranteed to rise from the east tomorrow. It's 99.9999999, a lot of 9% true. So it's almost guaranteed to happen. So if I tell you this sentence, I tell you almost zero information. But if I tell you that the sun will rise from the west tomorrow, this will be a big news. So there's a lot of information. So the amount of information should be calculated based on the probability. And that's Shannon's idea. Okay, so now we know that the amount of information should be relevant to P. So let's call it I of P. Okay, this is the measurement of information. So how does this I of P should look like? So we want I of P to have the following properties. First, the information, the amount of information should be non-negative. So I of P should be larger or equal to 0. Second, if P is 1, P is 1 means that this thing is guaranteed to happen. If this is the case, then basically observing this event tell us nothing at all because it's guaranteed to happen. So there's no information at all. So in this situation, we want I of P to be 0. And third, for two independent events, E and F, and their probabilities are P and Q respectively. So we want that P and Q to happen, P and Q are both happen because they are independent. So the probability that they both happen should be P multiplied by Q, right? So we want that I of P multiplied by Q is I of P plus I of Q. Okay, that's the third thing we want to we want to have. And finally, we want the information measure to be continuous and is a monotonic function of the probability. Continuous means that it's differentiable, and monotonic function means that it's always increasing or decreasing. And in this case, because when p is larger, we want the information to be smaller, so it's monotonically monotonically decreasing. Monotonically decreasing means that its shape should look like this. Let me open the pen. Okay. Monotonically decreasing means that this is p, this is I of p. So, and p is always between 0 and 1. Okay. So as p becomes larger, I of p always becomes smaller and smaller. It could be like this, or it could be like this, or it could be like this, or it could be like this. But anyhow, it cannot go like this, because then in this part it's not monotonically decreasing. So if you have upward parts, then that's not monotonically decreasing. So monotonically decreasing means that if P1 larger than P2, then I of P1 has to be larger than I of P2. That's I'm sorry. Yes. If P1 is larger than P2, then I of P1 has to be smaller than I of P2. That's monotonically decreasing function. And Shannon found that if we define I of P by this formula, then it follows all these properties. Okay, so I of P is log 1 over P, or negative log P. Okay, and for the base, there are several choices. So if we use base 2, it's called binary information unit. Base 3 is trinary information unit. Base E is natural information unit. Okay, and in this course, unless otherwise mentioned, we usually use base 2. Okay, so I'll give you some example. If you draw a card at random from a standard card deck, and if you get a spade A, how much information you get? So I said that the information is measured based on probability, right? So the probability of getting a spade A in a standard deck is 1 over 52. So I of P would be log the inverse of P. So it's 52 divided by 1. So this is roughly 5.7. Or you could use negative log 1 divided by this, which will give you the same thing. Okay? And if the card is heart, how much information you get? So the probability of getting a heart is 1 over 4, right? So P is this. So I of P should be, you could either use log 4 over 1, which give you 2. Okay? So let's look at this 5.7 and 2 and think about it. Which give you more information? If I tell you that the card is spade A, I give you more information. If I tell you it's heart, I give you less information, because heart is more likely to happen. Or maybe let me give you another. Let's not say heart, let's say spade. Perhaps it's more clear. Again, the probability that you get a spade is 1 over 4. Okay, spade, if you don't know what is spade, is this. It's spade. So if I tell you that you get a spade A, of course I tell you more information than I tell you just it's spade, right? Of course this gives you more information, and indeed this 5.7 is larger than this 2. Okay, so entropy, so finally let's talk about what is entropy. So I just tell you how to measure information, and entropy is an expected amount of information. So if we have n events, a1 to an, and their probabilities are p1 to pn respectively. So of course, summation pi has to be 1. And if we observe a certain ai, then how much information we get? We get log 1 over pi, right? So this is based on our earlier definition of information. And now we know that the probability of observing AI is pi. So what is the expected amount of information we will get? Okay, so what we should do is compute this. So what is this pi? Anyways, what is this? So what is expected value? What is the, let's say, so expected value is for example, what is, if I tell you that a certain xi follow a probability p, then what's the expected value of, for example, xi squared? That should be what? That should be it. If this is a, let's assume that xi is discrete. A discrete number. I'm sorry, a discrete variable. Maybe I should say this probability function is discrete. So E of xi squared would be summation p of xi multiplied by xi squared, right? This is by definition. What's the definition of expected value? So basically, you just compute every xi squared multiplied by the probability of xi, right? If so, for example, let's say throw a dice. Okay, throw a dice. The face of dice has 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And let's assume that their appearance, this is xi. And their corresponding pi's are, let's say, 1 over 6, 1 over 6, 1 over 6, 1 over 6. And here I have, let's say, 1 over 12. And what's the remaining one? It should be 3 divided by 12, right? Okay, then if I ask you what's the expected value of xi squared, okay, then there should be 1 squared multiplied by this plus 2 squared multiplied by this up to 5 squared multiplied by this plus 6 squared multiplied by this, right? So that's why we have pi multiplied by xi squared, right? Pi are these things, right? And this xi squared are these xi squares. Okay, so what's the expected value of information? Okay, so we have these are the probabilities here, okay, the pi's, and this is the value, right? The value of information. Okay, so so this log 1 over pi is negative log pi. Okay, so we have this. This is our definition of entropy. So entropy is the expected amount of information we get if we have n events, a1 to an, and their corresponding probabilities are p1 to pn. Okay, okay, so you have to memorize this for a moment. Entropy is negative summation pi log pi. Okay, now it's 3:51. Let's take a 10 minutes break. We'll come back at 4:51. I'm sorry, 4:01. Then it's hard to predict the result. On the other hand, if the coin is very unfair, then predicting the result becomes easier. If you know that this coin is 90% head, 10% tail, then it's more likely to get a head. Okay, so it's an easier predicting task. So now we said that entropy is the amount of expected amount of information. And we also said that if a certain thing is more likely to happen, then it gives you a smaller amount of information. Okay. So in these two cases, case number one, the uncertainty is high, so it has a higher entropy. On the other hand, in the second case, the uncertainty is lower, so it has a smaller entropy. Okay. So if we have an uniform distribution, okay, which means everything is equally likely, then it's harder to predict the result, which means the uncertainty is higher, which means high entropy. So for Gaussian distribution with smaller variance, means that the figure for different axes, and this is the P of x, okay, is something like this. Okay, this is a Gaussian distribution with small variance. Then you are almost certain that the values will be close to this. Let's say this is 10, for example. You are almost certain that the value will be 10. Maybe if the let's say this is 1, then you are almost sure that this would be probably between 7 and 13. You are very sure that the result should be within this range. Okay, so it's easier to predict because you know the value is probably 10 plus or minus. So it has low uncertainty, so it has low entropy because everything is very certain. Okay, so let's talk about the range of entropy. If we have n possible situations, then the maximum entropy would be log n, and it happens when everything is equally likely. When every pi is this, then everything is equally likely. Then in this situation, you will get the maximum entropy, which is log n. Okay, so you could use the let's say n equals to 2, and we say that entropy is defined as the negative summation pi log pi, right? So now we have two cases, which means p1 is p2 is half. So if you plug in this, you would end up having negative summation log, right? And I should write plus, right? And there would be negative. I don't need this summation because I write everything in this inside this parenthesis. Okay, so what is this? Is simply -1, right? So we have plus, okay, which gives us 1. Okay, so indeed it is the case. And the minimum value is 0. This is when a certain pi is 1 and pj is 0 for all j not equal to I. Okay, so this is when everything is certain. The result is always AI in this case. So in this case, we have 0 entropy. The expected amount of information is 0. Okay, so I'll skip this example. This is an example illustrated in a book called Shenlong Game, and it has a Chinese translation called 人性较量. If you're interested, you can read it by yourself. This is a very interesting book talking about most of this book is related to information theory and some of the what's that? What's the name of that? You know that what's the name of the test? Trying to determine whether the person behind the screen is really a person or a computer, I suddenly don't remember the name of that test. A Turing test. Turing test. Okay, Turing test. Okay, this is a book talking about Turing test. Okay. Anyways, I'll skip this example just to save some time, because I just want you to know the main concept of entropy, and then we will move on to the main dish, decision tree. So anyhow, information entropy provides a possible way to measure the amount of information, and it's based on the probability. So a highly certain event gives you little information. And we will use the information entropy to build a decision tree classifier later. Okay, so a quiz. Calculate the entropy of the following cases. First one, 2 positive and 2 negative cases. Then what's the expected entropy? Okay, so half of them are yes, half of them are nil. So which means P1 equals to P2 equals to 1/2. Okay, and n equals to 2. Okay, so if you compute the entropy, this is the result. Okay. How about all 0? They are all the 4 cases belongs to the same class. Then you know that P1 is 1, P2 is 0. So one way to do it is you just plug in the formula, or you know that when everything belongs to the same class, there's no uncertainty at all. Everything is very pure. So we know that there's no information. So the entropy is 0. How about this? We have n equals to 4. You have 4 cases. I'm sorry, 4 different classes. We have 8 samples and only 4 classes. And in this situation, what's the result? Again, one way to do it is use this formula. Or, as we said earlier, the maximum entropy would be this, right? Log n, where n is the number of classes. So here, we have 4 classes, and they are all equally likely. So you will have log 4, which gives us 2. Okay? We finished the introduction of entropy, and let's move on to the main dish, which is decision trees algorithm. Okay, and again, let me make sure that OPT is running correctly. Something wrong, because the screen seems to be larger than that. I need to fix this a little bit. Okay, it looks good now. So let me talk about decision tree classifier. So again, let's use an example. Let's begin with an example. So here we have 4 instances, and they are training instance. And let me open the pen. Okay, and we have 4 features. And this is our target. It's a binary classification problem. We want to predict based on 4 weather conditions. We want to predict perhaps whether a baseball game will play or not. Okay, so our goal is somehow we can build a decision tree like this. If we can build a decision tree like this, then we can make predictions. For example, if given this situation, and then assuming that we build this decision tree already, then we can see the outlook is rainy, so we go to here. And then the wind condition is true, so we continue to go here. So our prediction is no. the baseball game will not play. Okay. So this is simple once we build a tree, but how to build a tree? Okay, we want to build a tree based simply on the training data. Okay. So back in perhaps the 1980s, there was a once very popular method called expert system. So expert system also built something like this, build a tree something like this. But in those expert systems, the rules, the patterns, they are enumerated by experts. Okay, so again, that is sort of like rule-based algorithm. You tell the computers all the rules enumerated by human beings, and because the computers just memorize all these things, then it can again have a tree like this. But this tree, the rules are generated by people, not by computers. And now we want the computers to just look through all the training data and build a tree by itself. Okay, that's a main difference between a decision tree and a expert system. Okay, so the key question: how to generate a classification tree? Okay, so it's a greedy algorithm, which means that we make some we grow the tree based on some information, and once we decided, for example, we want to ask the question first, we cannot move back. Once we decide this, then we have to, based on this information, and continue to develop the tree based on this setting. If later on we found that this is probably not a good choice, we cannot regret this decision. So that's why it's called a greedy based algorithm. It tries to find the best possible situation currently. It may or may not be the best situation globally, but it's the best we could do so far. So it's a greedy based algorithm. Okay, so initially everything is at the root, but we will partition the training data to different groups and recursively doing this process. So let me give you an example as a start. Let's assume we have 3 reds and 2 blues. I'm sorry, 2 greens. And let's assume that this is perhaps they are sick, okay? And this is normal. And then assume that we can use a certain test to divide the 5 people into 2 groups. For example, this might be a certain measurement, let's say you measure the BMI is larger than a certain value or not. Okay, this means BMI is larger than some value, and this is when BMI is smaller or equal to certain value. Okay, then you have 2 groups. Again, you have these 3 sick people and 2 normal people. You use another measurement. Okay, this is F1. F1 is BMI. This is another measurement, F2. And based on this measurement, you can group people into 2 groups. The first group has 2 normal people. The second group has 3 sick people. Then F1 is a better way to divide the 5 people, or F2. It should be F2, right? Because if we use F2 to group people into 2 groups, every group is very pure. Pure means that if in the future, based on this rule, a certain people is falls into this group, we are more sure that this should be a normal people. This should be a normal person. On the other hand, if a future person comes in, and based on this F1, it goes to this group, then we are not very sure that whether this new person is a normal person or a sick person. It's less certain, right? So this is a better way to divide people into 2 groups. But this is a this is a very simple example because all the results here are very pure. So we know that this one is better than this one. How about in a more realistic scenario where each group may have some reds and greens? Then in these situations, how to define which features or which division are better divisions? So we use the concept of entropy. Okay, so this is the formula we introduced earlier. Entropy is negative summation pi log pi. Okay, so we use info to denote entropy. So let's look at this example. If we have 3 reds and 2 greens, how much entropy do we have? And we use information because we said that entropy is the expected amount of information, right? Okay, so we use info D. D contains 3 reds and 2 greens. So that means P1 is 3 divided by 5. P2 is 2 divided by 5. Okay, so we use I32 to denote 3 reds and 2 greens. 3 and 2. So based on this formula, we will end up having negative 3 over 5 log 3 over 5. Subtract 2 over 5 log 2 over 5. So this is the amount of expected amount of information, or the entropy. And we said that entropy can be regarded as the amount of randomness, or the amount of chaos. Okay, so this is very random. Okay. On the other hand, if everything is red, this is very pure, right? So we hope that the entropy in this situation should be very low. Okay, and let's calculate it. So we have 5 reds and 0 greens. Okay, so P1 is 5 over 5. P2 is 0 over 5. So this is the how we compute the entropy, right? Okay, so this is log 1. Log 1 is what? 0, right? Okay, so this part becomes 0. How about this part? We have a 0 here. But what is log 0? This part is log 0. Log 0 is negative infinity. So what is 0 multiplied by negative infinity? Okay, it seems, I'm not sure whether to find it or not. But here, let's make a rule. The rule is that, let's erase everything. Let's make a rule which is 0 multiplied by, or 0 log 0. We define it as 0. Okay, if we define it as 0, then we will have 0 subtract 0, which is 0. Okay, so we have no problem now. So okay, so we said that this should be very pure, which means the amount of randomness should be very low, and indeed we get 0. So this is what we want. Okay, now let's look at more realistic example. Now, assuming before a certain split, we have 3 reds and 2 greens. And now we divide these 5 people into 2 groups. And the division is based on feature A. Okay, if you remember, attribute is feature. Okay, we divide this based on feature A. So here is, if feature A is larger than a certain value, then it belongs to this group. If feature A is smaller or equal to a certain value, you belong to this group. Okay? And what's the randomness at this part? What's the amount of information in this part? That would be info 1 1. Okay? Info 1 1. And here we have 2 reds and 1 green, so that's info 2 1. And because 2 out of 5 are here, 3 out of 5 are here, so we sum them up with these weights, 2 over 5 and 3 over 5. And then we get the result 0.918, which is, if we split the 5 people into 2 groups, such that the group number 1 is 1 red and 1 green, group number 2 is 2 reds and 1 green, what's the amount of information after the split? Okay, so for 5 of them, we have info 1 1. For 3/5 of them, we have info to 1. So this is the amount of chaos after the split. Okay, and in the previous slide, we have computed that before the split, if we have 3 reds and 2 greens, the amount of the entropy is 0.971. After the split, the amount the entropy is 0.918. So the value of pureness improved by how much? By this much. This is the chaos, the amount of chaos before the split. This is the amount of chaos after the split. So the pureness improved by this much. Let's look at the second example. Again, we have the same 3 reds and 2 greens. And if you split these 5 people based on another attribute or another feature, and it turns out that 2 greens belongs to one group, 3 reds belongs to another group. So for these 2 greens, what's the entropy? It's info 20, right? Which gives us 0. How about here? We have info 30, which again gives us 0. And you need to use a weighted sum. The weights are 2/5 and 3/5, which are here. Okay, so after the split, the expected amount of information is 0 because everything is so certain. When you are in this group, you are green. Whenever you are in this group, you are red. So there's no randomness. The result is very, very pure. Okay, so the amount of randomness is 0. So how much improvement? The improvement in terms of pureness. Before the split, the amount of randomness is 0.971. After the split, the amount of randomness is 0. So we improve by the pureness improved by this much. And we want that after the split, the result should be as pure as possible. So which one should we use? If we can only choose from feature 1 and feature A and feature B, we should choose feature B because that gives us a purer result. Before I move on, let me check if there's any question on the chat room. Okay, no question. Let me move on. Okay, so that's the essence of decision tree algorithm. Okay, so we use a greedy algorithm because every time, maybe let me give you another example, and that's you'll probably see more. Let me give you another example, which is where is the example? Let me give you another example, and we'll come back to this descriptions. Okay, here's the example. Here, how many instances I have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay, I have 14 training instances. And I have 4 features. And this is the target. So I want to predict whether a customer will buy computer or not based on 4 features. The age, income, student, whether this is a student or not, and the credit rating. And I want to build a decision tree like this, or something like this, based on this training data. So how should I do? Okay, so we said that first you need to compute the amount of chaos before the split, right? So how random is it before the split? So here we have 1, 2, 3, 4, 5. We have 5 no's and 9 yeses. Okay, so let's say positive class is yes, negative class is no. So we have 9 yeses and 5 no's. So that means we have info 9, 5. So we have P1 is, or P positive is 9/14. The probability of the negative class is 5/14, right? So we just plug in the entropy formula, and this is the result. So before the split, how random is this? It's this much based on entropy. This is how random it is, 0.940, which means this is fairly random. Okay, now we want to test which feature gives us the best purest result after the split. So we start from age. See, if we use age to split the people into certain groups, how pure is the result? So age has youth, middle-aged, and senior. So we have three different values in age. Okay, so let's see. For the youth, 2 of them buy computer, 3 of them don't buy computer. For the middle-aged people, all 4 of them bought the computer. For the senior people, 3 of them bought the computer, 2 of them don't buy the computer. Okay, so what we need to do is we need to compute the entropy in each group. So group number 1, we have info 2, 3. Okay, group number 2, we have info 4, 0. For group number 3, we have info 3 and 2. Okay, and we know that this is 0. And this is 0.971. Okay, you just plug in the formula, which is summation pi log pi, right? And in this example, the P1 and P2 are 2 over 5 and 3 over 5 respectively. Okay, and here, this is here. Okay, so this is the amount of chaosness after the split, but we have to use a weighted sum because 5 out of 14 are in the youth group. 4 out of 14 are in this middle-aged group. And finally, 5 out of 14 are in this senior group. So we use a weighted sum of these 3, and this is the result. This is the amount of chaosness after the split. Okay, so I just tell you that here is what does this mean? What does this mean? This 5 over 14 means that 5 out of 14 instances belongs to this group. And this I23 means that out of these 5 people, 2 of them are positive, 3 of them are negative. So we need to compute info 2, 3. So how much improvement in terms of the purity score? So before the split, the amount of chaosness is this much, 0.940. And after the split, the amount of chaosness is 0.694. So the pureness score improved by this much. Okay, this is called information gain. Information gain. Similarly, so this is if we use age to divide people into 3 groups, then we will improve by this much. If we use income as the attribute to split people into several groups, so let's go back to the original training data. Income has high, medium, and low. So we will divide people into 3 groups. Okay, if we use income, high, mid, and low, and we need to compute the number of buy and yes and no, buy and not buy. Okay, so for high income people, we have 1 yes, 2 yes, we have 2 yes and 2 no. Okay, for the medium people, medium, this is yes, no, yes, yes, yes. How many yeses? 1 yes, 2, 3, 4 yeses. And how many no's? 1 no, 2 no, 2 no's. And low has 1 yes, 2 yeses, 3 yeses. I think we have 3 yeses. And how many no's? low income, we have one no, just one no. Is that correct? Let's see. For yeah, I think that's correct. Okay, so you need to compute info 2 here, and info 4 2 here, and info 3 1 here, right? And then you have to use a weighted sum, which means let me erase something and draw something, because that's too much things here. So let me erase this part and this part. Okay. Pen. Okay. So this has to multiply by 4 over 14. This it has to multiply by 6 over 14. This has to multiply by 4 over 14. And you just add them together. Add them together. And that should give you a entropy. And then that's this, okay? And the information gain is before the split, subtract the entropy after the split, and this is the information gain. Oh, I'm sorry, this is age. And likewise, you can get so income. This should be info D subtract info income D, and this is what we computed earlier here. Okay, this is the entropy if we use income as the criteria to split people into groups. Okay, and likewise you can compute the information gain based on people's identity, whether he is a student or not, and you can again split people based on the credit rating information. Okay, and because we have 4 attributes, so we can compute these 4 numbers. And it turns out that if we use age to split people into groups, it gives us the purest result. Purest because the purest score improves most. Okay, so we will use age to divide people into 3 groups. Okay, so this is what we get. For all the youth people, you come to this table here. For all the middle-aged people, they are here. For all the senior people, they are here. And now you don't need to consider age anymore, because all the people in this group, they are all the youth. All the people in the middle group, they are all middle-aged, so you don't need to consider age anymore. And all the people here are senior. So next, we need to consider from these 5 people, which feature you should choose such that the result is the purest. Okay, and this is simple because by just observing the data set, I know that student will give you the purest result, because if you don't have student status, you won't buy the computer. If you are a student, you will buy the computer in this group. So of course you can compute the information gain based on income, student ID, and student or credit rating. And it turns out that student should give you the largest information gain, which means that the next question should be student. Yes or no, right? So student, not student, not student. And you will have 2 yeses here, and you will have 3 no's here. And in this situation, the entropy is 0, right? You have 2 yes here, so the entropy here is 0. The entropy, 3 no's here, the entropy is also 0. So a weighted sum of 0 and 0 is also 0. And for the middle group, or middle age group, okay, again, this is the purest result you could get. Everything is yes, so the entropy here is already 0. Okay, so it won't continue to split. Okay, and then again, for the senior people, you need to compute which of the 3 features give you the largest information gain, and you will use that feature to split people into groups and continue. Okay. So let me check if there's any questions so far. Okay, no more questions. Great. So let's go back to the, after the example, let's go back to the explanations, which will probably give you a, you will probably have a better sense after this example. Okay, so we said that first, it's a greedy algorithm because every time we just look through the available features one by one and see which feature give us the best result so far, and we will pick that feature. So that's a greedy algorithm. And when should we stop partitioning? One possibility is that if all samples belongs to the same group, belongs to the same class, then perhaps we should, well, we simply cannot continue anymore. Okay, and the other possibility is that if we tried all the attributes and there's no more attribute that can continue to participate the data points, then we need to stop there. Or if there's no sample left, of course we cannot continue anymore. Okay, and how to split? We define the split. We sort of evaluate a split based on a goodness function, and in our example we use the gain to decide which feature give us the best result. And information gain is essentially the entropy before split. Subtract the entropy after split. Okay? Okay, that's the information gain we just introduced. And that's used by the ID3 decision tree classifier. And there's another thing called gain ratio, which is used in C4.5. And there's yet another thing called Gini index used in CART. And we will introduce these different goodness functions later. And how to split a tree? So certain decision tree algorithms, they allow canary splitting. Canary means that so when we say income can be high, medium, or low. So this is a trinary split. Okay? In certain decision tree algorithm, they allow only binary split. They doesn't allow this canary split. So in those situations, if you have an income which is high, medium, or low, you could only ask questions like, income is low or not? Okay, then if income is low, you are here. If income is not low, then these two things belongs to one group. So it's a binary split. And when to stop the further splitting? Okay, I talk about a couple of situations, and it is also possible that when your tree is too deep, you just stop continuing to grow in the tree. You just stop continuing growing the tree. And how to do the labeling? Once you build a tree, how to decide when you traverse a tree and when you arrive at a terminal node, how to decide the label of the nodes. How to decide the label of an instance that is in a certain terminal node. So basically, we just use a majority voting. Okay, so how to use a tree? This is obvious. A direct way is just traverse the tree. A less indirect way is convert a tree into if-else rules. Okay, and this is a property of entropy. We talked about it already. So if we are dealing with a binary classification problem, then when when both cases are equally likely, we have the highest entropy, which is 1. If one of the if the probability of a certain class is 0, the other is 1, then we have the lowest entropy. Okay, so this is how we compute the expected information after a split. Okay, and this is how we compute the information gain, which is the entropy before the split subtract the entropy after the split. Okay, and this is the example we just talked about. Okay, so before I continue, again, let's do some quizzes. Which of the following has a higher entropy? Okay, and of course, one way to do it is you just plug in the formula. Okay, so this one would be summation negative log. Plus. Okay, this is case number 1. Or likewise, you can compute the this and this. But even without computing, you should know the answer, because entropy is a measurement of chaosness. So which one has the highest entropy? It should be this one, right? Because you have half and half. This is the most chaosness you could get. And this is the lowest entropy, right? Everything belongs to one group, so it's very certain, so it has the lowest entropy. So even without computing anything, we know the entropy should be this is larger than this, which is larger than this. If you have two ways to group the 3 reds and 2 greens into 2 groups, based on the information gain we just introduced, then the decision tree algorithm will choose to split based on attribute A or split based on attribute B. The answer is very obvious. It should be B, right? Because it gives us the purest result. Okay, now next let's talk about some other ways to compute the chaosness or pureness or pureness. So the first one we want to talk about is gain ratio. So information gain measure is biased toward the attribute with a large number of values. So let's consider a very extreme case. Let's assume that we have a unique ID to every row. Then apparently if you group the data points based on their IDs, it will give you the purest result. What do I mean? What I mean is that assuming that you have a certain thing called ID here, and you have ID 1, 2, 3, 4 up to 14. Then if we split the data set based on ID, it will certainly give you the purest result, because based on ID, if it's 1, then the answer is no. If it's 2, the answer is no. If 3, the answer is yes, and so on. 14 is no. This is the purest result because every terminal node has one instance. And if that's no, then of course P, this is info 1, 0, and the entropy is 0. In the second case, again, this is I, 1, 0, so the entropy is 0. This is again I, 0, 1, and the entropy is 0, and so on. All the entropies are 0. So of course, after the split, the result is very pure, and the information gain is simply the chaosness before the split, subtract 0. Okay, so that's why I say that the information gain tend to bias toward the features with a large number of values. Okay, So in order to unbias this situation, we define something called gain ratio. So gain ratio is information gain of A divided by the split information of A. So what is the split information of A? Let me give you an example directly. Okay, so if we use income as an example, the number of income equals high. The number of high income people is 4. The number of medium income people is 6. The number of low income people is 4. So we use this 4, 6, 4 to compute a entropy. Okay, so we have 4 divided. We have info 4, 6, and 4. Okay, which give us negative. This formula here, negative 4 divided by 14. So we have P1, P2, P3. They are 4 divided by 14, 6 divided by 14, and 4 divided by 14 respectively. So this is the formula, and so this is called the split information of income. And so the gain ratio is defined by the information gain of income divided by this split information. And you can see that if you have a lot of different, if we have 14 IDs, right, ID number 1 to 14, then what is the split information of using ID? Then we will end up having negative 1 over 14 log 1 over 14 subtract we have essentially 14 such terms, right? So essentially this is P1 equals P2 equals P14 equals 1 over 14. Right, and we know that in this situation you would end up having the maximum entropy. Right, we have 14 cases, and in fact that's log 14. Right, I don't know the number, but it's probably 3 point something. Okay, so that's we have the one. Oh yeah, so that's 3 point something. 3 point something, right? So if we use the ID to split data set into certain groups, that will be penalized by this much because we divide it in the denominator. Okay, so we sort of trying to select a feature that would make the result as pure as possible. At the same time, we don't want the feature to have too many values, because if a certain feature has many distinct values, that means after the split, the result tend to have lower entropy. Okay, because every group has fewer people, right? So we want to unbias that situation. Okay, so so it's 4:51, so let's call it a day. And before I finish today's lecture, let me make sure that there's any questions in the chat room or not. Okay, I don't see any question on the chat room, so let's probably call it a day. I'll stop here.